Hi, my name is Marius Bock, and I'm excited to present our paper, Improving Deep Learning for Human Activity Recognition Using Shallow LSTMs, which was joint work with my colleagues Alexander Hölzemann, Michael Möller, and Christoph van Laufen. In our work, we revisited the popular DeepConv LSTM architecture by Ordonez and Roggen. To this date, the architecture is a state-of-the-art method for applying deep learning on human activity recognition. In our paper, we suggest to simplify the original architecture by removing the second layer of the LSTM, thus employing a one-layered instead of a two-layered LSTM. The LSTM is parameter-wise by far the largest part of the architecture. Omitting one LSTM layer thus resulted in a decrease of up to 62% in parameters and of up to 48% in runtime during experiments. Now, you might ask yourself, at what cost does this change come? How much does the simplification hurt the predictive performance of the model? Well, to answer this question, we compared the performance of our architecture to the original DeepConv LSTM architecture using 5 publicly available human activity recognition datasets as input. These datasets were the opportunity dataset, the wet lab dataset, the real-world HAR dataset, the SBHAR dataset, and the HHAR dataset. The datasets differ in the amount of participants, number and type of activities, and number of features being employed. To test both architectures, we also varied the number of hidden units employed within the LSTM layers. We employed either 128, 256, 512, or 1024 hidden units, which left us with a total of 8 architecture variations to be evaluated. We used leave one subject out cross-validation and used the same set of hyperparameters across all experiments. The hyperparameters were obtained based on tuning results from the wet lab dataset. Each variation was tested using a set of 5 random seeds and thus ran 5 times. The final result for each variation was then the average recall, precision, and F1 score across the 5 runs. An exception was made for the opportunity dataset, where we chose to use the same pre-processing and train test split as Ordonez and Roggen, and thus did not apply leave one subject out cross-validation. So, to come back to the initial question, how much of a decrease in predictive performance does one need to account for when using our simpler architecture? The answer is none. The predictive performance actually increases. As one can see with sample results obtained from the real-world HAR dataset, using our simpler architecture, performance significantly increases as far as precision, recall, and F1 score is concerned. Overall, our architecture continuously outperforms the original DeepConv LSTM architecture for the opportunity, wet lab, real-world HAR, and HHAR dataset, with recognition performance going up as much as 11.7% in F1 score. For the SBHAR dataset, our architecture is only on par when employing 512 and 1024 hidden units. Now, let's have a look at a statement which was written in a recent survey paper by Chen et al. On deep learning for human activity recognition. It says that the depth of an effective LSTM-based RNN needs to be at least 2 when processing sequential data. This popular rule of thumb is based on findings presented by Karpathy et al., which visualized and investigated how LSTMs learn within the setting of natural language processing. Nevertheless, during our experiments, we investigated an opposite trend and had architectures using a one-layered LSTM consistently outperform two-layered ones for 4 out of 5 datasets. The goal of our paper is thus to challenge this rule of thumb in that it might not be applicable to sensor-based human activity recognition. Now, to conclude this presentation, let's talk about how we made sure to exclude overfitting as being the reason for the witnessed predictive performance increase. In order to spot the degree of overfitting, we closely monitored the generalization gap, which is the difference between training and validation accuracy. The larger the gap, the more likely the network overfitted on the training data. We also made sure to use datasets which have both large and small feature dimensions and varied the type of activities which are to be predicted by including complex, transitional, and simpler periodical activities. All in all, we saw both architectures suffer equally from overfitting across all datasets. Lastly, our directions for future research are twofold. First, we aim to validate our assumption on larger human activity recognition datasets, for example extracted by using IMUtube. As human activity recognition datasets are relatively small in size compared to other deep learning datasets from other research areas, validating our claims on larger datasets would further rule out overfitting as being a reason for the witness performance increase. Second, we aim to apply the same analysis as Karpathy et al. Using human activity recognition dataset as input. Doing so, we hope to better understand and visualize the trend that we witnessed that one-layered LSTMs might be a better suited option when dealing with sensor-based data. Here's a list of all the papers which were mentioned in this presentation. And yeah, this concludes our presentation. Thank you for your attention. If you're interested in our implementation and our results, our architecture as well as everything to reproduce our results are available on GitHub. So just scan the code or type in the URL below and it will take you right there. Feel free to also contact me via email if you have any questions about our implementation. And yeah, thank you for your attention.